to the very first episode of the Koç University Undergraduate Journal of Engineering podcast. With this new series, our goal is to introduce you to the groundbreaking research and academic work of Koç University faculties. Today, I'm delighted to have with us Dr. Sajit Rao from the Department of Computer Engineering at Koç University. And I would like to begin with my first question. In what ways does embodiment enhance an agent's perceptual accuracy, concept formation processes, and action generation capabilities compared to purely disembodied systems?
Well, that question is quite easy to answer because disembodied systems don't have any sensors or motors at all. Right? So basically, they are sort of completely disconnected from the world. So there's no issue of improving perceptual accuracy because they don't have any to begin with. So in this case, basically any embodied system with even one sensor and one motor is obviously vastly superior to a completely disembodied system that is not even sensing the world in any particular way. So I think though maybe sort of a better question might be to get into what is the effect, when do you need embodiment, for what kinds of things? That might get more into the whole issue of embodiment. Because in this case, obviously, disembodied versus embodied, if the disembodied system has no perceptual capabilities, then it's kind of a moot point. But so let's talk about a few different kinds of problems and for which ones you may need embodiment and what kinds of disembodied solutions may or may not work. So let's say you're trying to build some smart AI program that is going to do stock trading, that look at the Turkish stock market and be able to predict the price of some stock on some day. So this kind of program, obviously, it can be completely disembodied. All it does is it basically sucks in the stock prices every single day. It does all these analysis based on history and all that. So it's completely disconnected from the world. It doesn't need to have physical sensors and physical motors. It doesn't need to move. It doesn't need to touch the world in any way. It's just getting data from the internet. That's it, right? So that's one example. Okay. And now, on the other hand, imagine a completely different kind of robot that needs to do surgery in a hospital, because there are robots that actually do surgery, right? Or robots that go into the deep sea, like a kilometer under the water to repair an internet cable that's damaged, because those are dangerous conditions for human divers to go so deep. So those are perfect for robots. So in both of these examples, the surgery robot and the deep sea repair robot thing, you need a physical robot. You need something which has physical existence, right? To go and, in surgery case, sort of poke something in you. In the deep sea case, grab the cable or do something to it. So this case, clearly you need embodiment. Okay, so this is the other extreme from the stock market example, where in that one, completely disembodied solution was fine. In this example, you absolutely need an embodied solution. So these are the easy cases, extreme ends of the spectrum, right? Now, but the interesting thing is the large class of problems in between these things, where, for instance, you're just asking a question of a system. For instance, you're asking the system, and how should I get from here to there, or some general question about the world. So in this case, this is the interesting range of questions where will a purely disembodied system do the job? So ChatGPT is purely disembodied right now, right? Yes, they're doing things called foundation models. They're training ChatGPT now better with images and video, but let's not get into that for now. But just imagine one of the early versions of ChatGPT, which is purely language-based. Okay? So ChatGPT was not really connected physically. That is, it didn't sense the world with eyes and touch and smell. Okay, it was just a disembodied model. So there are clearly some questions that ChatGPT can answer without being embodied at all. It answers many of them correctly. But the claim that I guess some people like me like to make, or I like to think, is there are many questions where being physically embodied in the world helps you better answer these questions about the world. So there are things like common sense questions. So let me give you an example. If you talk to like a 4 or 5 year old kid and say, I dropped my keys, where should I look for them? Should I look for it on the floor or the ceiling? Kid will obviously say, yeah, obviously the floor. When things fall, they go down, they don't go up. Okay, It's a very simple thing that is intuitive. It's so silly that a kid will think it's silly for you to ask such a question. But if you think about it, that is actually comes from our experience of the real world, right? If you didn't experience gravity, if you didn't experience things falling, by being in the real world and experiencing it, that's how the kid understood that intuitively because of that experience. But will a disembodied system know that intuitively? No. It won't. That's the point, that a disembodied system, ChatGPT will in fact answer that kind of thing correctly, but because it read it somewhere. You see the difference? That it read somewhere that when in words, that when something falls, then it goes down. So where is the meaning for? So this is the whole issue that people, there are really two very different camps in AI. Those that believe that just by reading words, meaning somehow comes out of it, that words talking about other words, you get meaning out of it. And there are others, more similar to me, who believe that purely words still don't tell you about meaning. So for instance, you can read a whole essay about water. Okay, ChatGPT can find hundreds and hundreds of essays on the internet about water. But ChatGPT has no idea of the feeling of being wet, ever, right? Actually, the feeling of being wet and what it means to be wet, whereas an embodied robot would, right? So I claim that an embodied robot will have a better intuitive sense of wetness and be able to answer that better. Okay, but that's just a hypothesis.
So some of the ways infants learn to see the world are really fascinating. What can those mechanisms teach us about improving embodied agents' perceptual learning?
So the thing about intelligence, intelligence is a very complex thing. And it takes time to build it. So nature has this amazing recipe. So we've evolved over millions and millions of years, and nature has kind of perfected one solution. It may not be the perfect solution, but it's a very good solution for how intelligence develops after birth. Clearly, a newborn infant, it doesn't have adult level intelligence, obviously, right? Why? Even that's kind of why is that? Why aren't infants born with huge, they have pretty big brains. Those brains, by the way, have a lot of neurons. Okay, it's not like it has any less neurons than many adults. So why isn't it born completely, fully intelligent, able to completely? So there are reasons why, because it needs to learn a lot about its environment, and nature staggers the learning, which means some things mature first and they lead to the maturation of other things. Okay, so for instance, visual capabilities mature very quickly in an infant, very, very quickly. By about 6 to 8 months of age, the visual part of their brain is indistinguishable from an adult's visual brain. But clearly, language takes more time to come. It's only around the age of probably 18 months or so that they start speaking in 2-word sentences. Why does the language take so much longer? So one of the hypotheses in cognitive development is that basically that you need that kind of experience to get concepts in the world, non-linguistic things, so that later when you say the word, dog or ball, you can actually attach it to perceptual meaning and motor meaning, right, for words. So you need that experience first so that you can actually attach meaning to words. Okay, so basically, the point is that cognition is staged like that, step by step, where one thing kind of leads to the other. So even within vision, actually, there's some very interesting work done. Even not just vision leading to language and meaning, but there's even within vision, there's some very nice work done by Shimon Ullman's group for one, and many other groups as well, which show, for instance, how infants learn to detect what someone is looking at. Okay, so there's this thing, basically humans, one of the big, very sort of strong cognitive capabilities of humans is to assess the intent of another person. How do they do that? One of the big cues they look for is what the other person is looking at. So, and we do this all the time, even unconsciously. Even when you're walking down the street, you may be talking to your friend, but believe me, your eyes are scanning and quickly looking at other people's faces and where their eyes are looking. and you are there and making inferences about what their intentions are towards you, simply based on where they're looking in their eyes and what they might be, or what might be going on in their heads. Right? Turns out that it's a very important skill that humans need to pick up. Infants pick it up very quickly. Not just human infants, even macaque monkeys. Okay, need this. It's very important for their social behavior to be able to look at another macaque monkey's face and know what it's looking at, okay, or who it's looking at, and make inferences about what to do based on the state of the other macaque monkey. So it turns out that if you think of it as a computational problem, as a machine learning problem, how can an infant learn to find the face or eyes of somebody and then detect where they're looking at? It's quite a complex problem. All the things in the room. Okay, even if my head is pointing in some direction in the room, there's still quite a lot of things in that direction, right? So how can you train a machine learning system? So in a machine learning system, you have an input and you have an output, and you have to do, let's say you're doing supervised learning, let's say, and you're matching it. But what is the supervision signal here? Somehow, even if you've got the eye position from images, you need to know what those eyes are looking at, and these images come unlabeled. Okay, so you need basically you need to do unsupervised learning, and so through some very nice experiments, there's some groups that have shown that the way infants actually learn that is, first of all, they can find eyes innately. It's really important for human infants to be able to find their mother's face. It's kind of built in. That does not have to be learned. If they're born, they can find faces. Okay, but after that, around 6 to 8 months of age, infants start looking away from the face to your hands. It happens around 6 to 8 months of age. So now they start finding your hand, other people's hands, interesting. Okay, so that happens, and then it just happens. So once they detect hands, and that develops, that they can detect hands in the scene, it turns out that now, and since they can already detect faces and eyes, okay, now they start correlating. There's a training signal. They kind of assume that when somebody is holding something or doing something with their hands, that their eyes are looking at it, which most of us do. Like usually when you're doing something with your hands, you're looking at what you're doing. It's rare that you're looking somewhere else and doing something here, right?
Yes.
So that's kind of built in. Now you suddenly have a training signal because the infant knows the sort of eye direction and just assumes that it's the hands that are of interest. So it now has a training signal. The eyes must be looking at the hands. Mm-hmm. And so now you automatically have a training signal to train a neural network that maps eye position to object position in space. It's always the hands. So it's trained only on hand position, okay, with the eyes, and it gets good at predicting that. Then it can generalize to other things outside. So this is stage development. This is exactly how in embodied systems, staging the development of figuring out what someone is looking at. It would be too hard to do it from scratch. But the moment you break it up into two problems, first find the hands, then train on the hands, and now you have a system that can look somewhere else, really makes it much easier to learn. Okay? So this is an example that I like a lot of how in embodied cognition, you can chop up the learning problem into more manageable pieces than if you did it in a purely disembodied way. Having said that, it's actually hard for us to know how to do that. How do you chop up the problem? We don't really have any good science for doing that.
What are the key differences in concept formation mechanisms between humans and current embodied agents?
So, current embodied agents, they're actually very, very different. Probably the major ones are that we are very good at learning from individual examples. Because think of, when you're an infant and you're learning the difference between cats and dogs. Take a very simple thing of all the things. Okay. In machine learning, the way you would do it is you give 100 examples of cats, or thousands actually in images. You get thousands of examples of dogs. Okay. And then in the supervised learning, at least, you say that. You can also try to do it clustering in an unsupervised way, but let's keep it to supervised learning for now. But the things you have to give them in batches. You can say, here's a batch of cat examples, here's a batch of any, or labeled, basically, it doesn't matter. The point is you have to do batch training in these things. But the real world is not so cooperative. If you put a robot in the real world and just let it go somewhere and say, okay, learn about things called cats and dogs. It may see a dog, nobody tells it it's a dog. Okay. Then it doesn't see another dog for like 6 hours, during just which time it may see 5 or 6 different cats. Then it sees another dog again, which looks quite different. Okay. So examples come along individually. They don't come in nicely collected batches that we need for sort of machine learning training. So humans are extremely good at learning from few examples that come intermittently, and our entire paradigm of machine learning is not built for that right now. Okay, so there's a huge difference right now, right there. Basically, unlabeled examples that come in batches. So that's one thing. The second thing is that humans can grab data by themselves. They can explore things that they don't really understand. Babies do this all the time, by the way. So if you notice, you give a baby a toy, a new toy, right? First thing it'll do is it'll look at it everywhere, then it'll bang it, okay, then it'll try to eat it, okay, it puts it in its mouth, it's exploring it to see whether it's edible and all kinds of things. And it gets really, really interested in this thing, and it just does all kinds of things with it to see what can you do with this new thing, right? So basically it's a new thing, it's surprising, and it really explores it, okay? And you can selectively put another toy that it may or may like, but something that it has explored many times before. It'll ignore that for a bit because this new thing is interesting right now, right? So what it's doing is it's selectively seeking data and using its hands to explore things that it needs more information about. Currently, with other kinds of machine learning, disembodied kinds of... So basically humans have to feed data to machines, right? If the machines don't have the opportunity to go and grab it themselves, okay, they're relying on a human teacher to carefully collect the data and feed it. It's completely different from the system itself grabbing the data that it needs, right? So this is a huge way in which embodied systems are quite different from currently sort of the disembodied kind of training that's going on. Okay, so I think I'm sure there are other ways. Another thing is is related to the first thing. This is called active learning. What I just said is active learning. So basically, embodied systems are active learners in the sense that they grab the data that they need from the environment. So in another, for instance, if you are a search and rescue robot, okay, or drone flying, and you see an area that you haven't explored before, then it will selectively go to that area and explore it. It can do that, right? Because it seeks new information about something it doesn't know. Okay, so that is active learning. And then the other thing is incremental learning. Basically, this thing related to what I said before. You learn a little at a time. Okay, they're very, very good at doing that kind of focused incremental learning. So these are some ways in which I think the sort of concept formation and learning is very different in embodied systems.
So which experimental paradigms have been used to evaluate concept formation in embodied intelligence?
So there aren't that many really. I mean, basically you have to test. So how do you test concept formation? Well, you test it either by asking it if it has language, or by behavior, by seeing how it behaves in circumstances that you set up for it to test, to see if it has grasped some concept, right? And this is what you would do, by the way. This is what you would do even to see for an animal. Like, for instance, suppose it's an animal, like, non-human thing that you think is intelligent, but you want to test it. A dolphin, for instance. Dolphins are very smart, right? Whales are very smart. But how do you test dolphin intelligence or whale intelligence? Okay, how do you test concept formation in a dolphin? Well, what you can do is so many experimental paradigms exist in psychology for that. You show it 4 or 5 objects every day. It knows, for instance, what it plays with them. It understands what each of. Then the 5th day, you show it a completely new object, and you see whether it has more attention towards that. Then you test it, for instance, 1 month later, where it still remembers that one new object you showed it or not, and you can test if it recognizes it or not. So that's completely behavioral because you can't speak to the dolphin and say, do you recognize it, right? Obviously, if you can speak to the thing, if you're speaking to a language model or something that has a language, you can directly ask it, right, and see what it says and test it that way. So in terms of paradigms of testing, there aren't that. I mean, basically, there's sort of linguistic. You can carefully come up with a bunch of questions that probe whether it has a certain concept, or you can carefully design a bunch of experiments in the physical world where you put it into a situation to see if it gets a concept. For instance, let's say you're trying to test whether an autonomous vehicle that can drive itself has actually grasped concepts about the world that it drives in. You may ask it to go to some destination, okay, and let's say there are multiple routes to that destination. But you also supply it with the information that, let's say the shortest route, there's a very sharp downhill portion of it, and let's say it snowed 2 days ago and it's very cold now. You just supply it with that information. Will it conclude that because it's downhill and it snowed and that road will be very icy and dangerous to go down, so even though that's the shortest route, it's safer to take a slightly longer route? You can test it, right? It doesn't have to speak to you. Okay, you can put it in these situations, right, where you can see its behavior and see the decision it makes in terms of action, right, and test it that way. So, yeah, I mean, basically, you just have to you either test it by behavior or language or both.
My last question will be, in which aspects of real-time sensory-motor integration do today's artificial neural networks fall short compared to biological systems? And what kind of architectural modifications might actually help bridge those gaps?
That's a hard one. I mean, if I knew all the answers to that, then I'd be doing all of that right now. Right? But yeah, no. One way, there are a few different ways. So one of them is that the brain basically operates in real time, sort of millisecond precision, with recurrent feedback loops in sensory and motor areas. So let's say you are manipulating a nice fine crystal glass with your fingers. Okay, you're twirling it around. With a little practice, you can get quite good at it, and you can hold up a glass and not drop it or crush it. Fine manipulation is something actually robots struggle with. Okay, like tying one's shoelaces, for instance, is something that kids get after a while. It takes kids also a while, by the way. Kids are very clumsy with their fingers. But in fine motor manipulation actually occurs fairly late in kids, probably after the age of 5 or 6 or something like that. It's one of the latest things to happen, where to have fine control with their fingers. But it does happen. But robots somehow are incredibly bad at that. The reason here that the brain has such a big advantage is because of the very fast feedback loops that we have, which are continuously, as we manipulate something, we get the sensory feedback, which immediately changes the actions that we are doing to it. The current artificial kind of networks of neural networks that we build aren't so adaptive in basically modifying what next action they're going to take based on immediate sensory feedback. So that kind of closed loop control, it's called closed loop control, where you have that kind of feedback on top of basically learning strategies. It's not a very mature field right now. Okay, so they can be pretty bad at it. So that's one thing. Another one is basically we are constantly adapting. Okay, so as the situation changes, our brain anticipates things. So our brain actually can run what's called a forward motor model. Okay, it means this. It means that, let's say I want to reach out and grab something. It's like it's on my desk, let's say, but my cup is now, let's say, over there right now. It's right there next to my screen. And exactly in the situation, it's actually slightly behind an obstacle. Okay. So rather than me immediately reaching out my hand, what happens is I play out in the part of my motor area where actually I play out a motor program, almost like a simulation of myself inside myself that I run, of me moving my arm, and then somehow that it doesn't work because my arm will hit a box. So then I change the program, and then I run it, and then I predict the final position, and it kind of makes sense. Then I run the program. Then actually I do it. So I have a forward model of how what my motor system is capable of. Think of it like motor imagination, and the sensory feedback. It's not just motor. I can imagine my arm moving close to the wall, and I can also predict the brush of the wall against the side of my hand. I can predict all of that. Okay, the brain does all that. It's amazing how much the brain does this kind of prediction before it does things. Okay, now artificial systems are still not great at that. They're much more reactive. They have a plan. Maybe they'll have a motor. They also make motor plans, but many of that, when something goes wrong, it's much more reactive at that point. Okay, so in that sense, we are still much better. Our sort of the models that we run for anticipating what the sensory feedback is going to be when you execute a motor command. We even predict what our senses are going to feel when we move our arm in a particular direction. Right. So we are very, very good at that, and this is an area where the sensory motor integration really isn't quite there yet in terms of that level of precision and prediction in artificial systems. In terms of what architectural changes need to be made to accomplish that, it's I don't know. I mean, there are ways you can try to play around with building systems where you have basically. I don't have a good answer for that. I mean, I can come up with some ideas of how you can do reinforcement learning and this and that, but they're completely experimental. And the true answer is that I don't really. For the sensory motor things, I don't really have a good answer right now for that.
That was the final question. Thank you, Hocam, for joining our podcast, and thank you for your valuable insights on embodied intelligence.
Well, thank you very much, Ipek, for interviewing me.